Hello everyone, welcome to Regina Astronomia. I'm your host Regina Kim and I'll be taking you to a guided star tour.
One please, for mankind.
Over this video, we will explore supernovae, red giant, white dwarfs, and even black holes. But before we step into evolution, let's take a step back. I want to talk about
fusion. Stars form from an accumulation of gas and dust, which collapses due to gravity. If the collapsing gas cloud is massive enough, the temperature and pressure in its core will increase until they are high enough to initiate the nuclear fusion of hydrogen into helium, with releasing binding energy. Stars on the main sequence are in the hydrogen to helium fusing phase, which lasts significantly longer than the other stages in a star's visible lifetime. The rate of fusion determines the luminosity of the star, and the main sequence stars with higher luminosity are hotter and bigger. Photons are generated due to the fusion reaction of hydrogen into helium-4. As these photons are released from the core, they collide with the surrounding material and thus establish a radiation pressure. The hot gas particles themselves also emit a gas pressure. These pressures oppose the effect of gravity, which would condense the star further if without pressure. If the outward pressure is too great, the star expands. Then the core temperature decreases and the fusion rate drops, so that the effect of gravity leads to a contraction. On the other hand, if the outward pressure is too small, the star contracts. The core temperature increases and the fusion rate increases. This then increases the radiation pressure, leading to an expansion. The new star then achieves a state of equilibrium. As the inward force due to gravity is balanced by the outward force due to the radiation pressure of photons with the gas pressure of the fast-moving particles. In this condition, the star lies on the main sequence, where it stays until fusion of hydrogen in the core can no longer sustain this equilibrium. At the end of its main sequence life, a star has a core of helium surrounded by hydrogen. This core is not hot enough for helium fusion to occur, and the outer layers are also not hot enough for hydrogen fusion to occur. Without fusion, there is no source of energy to balance out the gravitational pull. So the star will depart from the equilibrium state it has been in and start to collapse once again. As the core collapses, its gravitational potential energy is converted into kinetic energy of the particles. So the shell of hydrogen surrounding the helium core gets hot enough to start fusion. This shell fusing or shell burning of hydrogen produces a large amount of energy and causes the outer layers of the star to expand. As the star expands, it cools. This is the paradox. If you give the star energy, it cools down due to the conversion to potential energy, which causes a net drop in the kinetic energy of the particles. The star then becomes very big, up to 100 times its original radius, and its outer layers are relatively cool despite its very hot core. We call this a red giant. When the core gets hot enough for helium to fuse, two helium-4 nuclei combine to make beryllium-8, which quickly combines with a third helium-4 to make carbon-12. This is the triple alpha process. The fast speed of fusion causes the core to explode in what we call a helium flash. The core now consists of carbon surrounded by a helium shell. Then, core temperature is too low for carbon fusion to occur, and this causes instability, which makes the star enter a second red giant phase. One consequence of this is that the escape velocity of material in the surface is low enough that the energy is supplied by the shell fusion of helium. The outer layers of the star can be ejected into the surrounding space as a hot glowing ring of gas, known as a planetary nebula. In its final state, the star has a very hot degenerate carbon core, which is no longer able to sustain fusion reactions and balance gravity by electron degeneracy pressure. Because the core is now exposed, the remnant star is very small, about the size of the Earth, and very hot, around 200,000 kelvins, which we call a white dwarf.
That is how the low-mass stars that weigh less than 8 solar masses, including the Sun, end up in the universe. FYI, one solar mass is approximately 2 times 10 to the power of 30 kilograms. Now, let's take a look at heavier stars.
The main sequence of the evolution process is similar, but as a more massive star has a bigger surface area and a higher surface temperature, it has faster fusion rate and thus burns faster. More massive stars are more luminous due to fast fusion rate, but they also have shorter lifetimes. Another main difference is that the fusion process does not end with carbon, but rather a series of heavier elements such as neon, oxygen, silicon, etc. Thus, a red supergiant is formed. As a result of shell fusion and the supergiant ejecting its outer layers, the iron core grows, supported by electron degeneracy pressure until it reaches the mass limit. Gravity now wins, so the core collapses immediately, protons and electrons forming neutrons and neutrinos. This is a supernova, a powerful and luminous stellar explosion, reaching high temperatures and high luminosities. Then, a hard ball of neutrons with diameter of 10 km is formed, sustained by the neutron degeneracy pressure, a neutron star. The neutron degeneracy pressure that stabilizes a neutron star against gravity can resist the incredible pressure that results from the supergiant core being compressed into a sphere of radius around 10 km. But even this fails for higher masses. When the mass of a star on the main sequence exceeds 20 solar masses, it ends up as a black hole, an object so dense that its escape velocity exceeds the speed of light, so that nothing can escape.
This stellar evolution process takes a long time, maybe like 1,000,000 years. Mind-blowing, isn't it?